random variables here. So let's consider what is called acceptance rejection method. Okay, so let's see the case. So here, let's consider Z1, Z2, U1, U2 are independent random variables. So which means if you want to use acceptance rejection method, you need to have two kinds of independent random variables. Of course, you want to generate some random variable. That's your X. Okay, X is the one you want to generate. And then you will use some other random variable, have some common, which means this one is easy to get. So common density function rho Z. So Z actually is the one you want to use to generate your X. And then we need to use the uniform one. Here, let rho of X be the probability density function you want to generate. And you will introduce a constant C. And this one should be less than or equal to 1. Okay, be careful. This is an upper bound. So the ideal case is C is 1, but most cases you cannot do that if you use acceptance rejection method. And then you need to make sure this rho of X is the one you want to generate times C is less than or equal to rho Z for any Z, which means to density function, you plug any Z value inside, this should be true. Okay, it sounds a little abstract. We will see how to implement this, okay? And I will show you some example, then we can know how we can try to do that. So we start with I is 0, and then continue to I is n, okay? And then here, we will choose this, we'll use one is called WK, and say for K is 1. So you can see here, depends like the sample size you want to generate is n, but the number of random variable we need to use is using K to denote. So we have K is 1 and 2. So first one, so generate UK, generate ZK. So you plug ZK inside to two density function and check if this UK is less than or equal to this ratio, which means this is the chance of keeping this ZK. So if it satisfies that, you will keep this ZK. Okay, so WK is 1, which means you accept that, then let your XI equal to ZK. Otherwise, if it's not less than that, it's greater than this case, you will consider say let WK is 0, which means you reject that. Then you will increase K, but your I will still be the same. Is that okay? All right. So let's see the idea here. Okay, but actually the case is not to use rho X to compare with like C times rho X to compare to rho C, or actually is you use rho X, the density function you want to generate, to compare with rho Z divided by C. You know C is less than or equal to 1, so we try to make it a little bit larger. So why we want to make it a little bit larger is we try to put that above the density function of rho of X. And we hope it will have some intersection is where the ratio is 1. Okay, so this is the density function of rho Z over C. And then this is the density function of rho of X. So of course, if something close to this part, so Z3 here, you can consider this ratio is exactly equal to 1. So which means exactly equal to 1 means what? Means this UK is always less than or equal to that. So this Z3, we will definitely accept it. Does that make sense? Because actually this density is very close to rho of X. So we want to accept that. But if it's in some other case, then we need to check this ratio, and also depends on your U. So how do you know the density function of X? Okay, thank you, Xian. This is a very good question. So if we try to do that, we need to know the density function. Otherwise, you cannot do acceptance rejection method. So if you want to use acceptance rejection method, you need to know the density function of the random variable you want to generate, and you also need to have some other density function. This is the way how to use that. Maybe you will ask, if we already know the density function, why we don't use our inverse distribution transformation to find it? Maybe you cannot. So that's why you want to use this acceptance rejection method to do it. Is that okay? So this should be given. Otherwise, if it's unknown, and if you have no idea about your x, then you have nothing to do. Okay, or if you can just generate this in a black box, it's also fine. But here I try to give you the idea, because if the ratio is larger, so which means they're closer and closer, so this row of x actually will be considered to be closer and closer to this rho z over c, then you will have highly chance to accept it. Otherwise, if it's too far away, then the probability to accept that will be smaller, but still it depends on the uniform random variable, and then you try to consider to accept it. I will show you some example later. Okay, so the key idea here is actually how to find this c. That's the most important part for the acceptance rejection method. Okay, then let's keep doing this. Okay. And here you can see if z be a number in omega, the common sample space. So which means if you really want to use this acceptance rejection method, what you try to do is you will consider this rho z or rho x actually have the same common sample space. So which means if you try to generate some random variable on the interval, for example, -1 to 1, will you consider to use this acceptance rejection method with the standard normal random variable? No, because it's not so efficient. Because the sample space for for standard normal is actually negative infinity to infinity. If it's from -1 to 1, then what you try to consider is you will also try to find some z also on the same sample space. So that's the idea. Okay, so here, the PDF for the x generated by this accepting rejection method. So you will consider evaluate as z is equal to rho x of z. Now, of course, we will have some other parts here. So the density function we denoted as rho delta x of z because we introduced w inside. So we can consider this conditional on accepting the c for the next x, right? So given this, so we will evaluate at c, and then we try to consider to accept that. So only when w is 1, then we will consider to accept z. So this is the conditional on probability here. Then by the Bayes theorem, so we know we can do as consider given z, we have the value of w, and then 2 times the density function of rho z divided by the probability of this, like w is 1. So this is the mass function here. So we will rewrite this by Bayes theorem, right? So this probability, W is Z, actually is the probability of acceptance. And what is this one? This one is the massive function for acceptance given Z. So evaluate at Z. So we try to rewrite like that. And then this actually is the ratio of what we have, rho of x, rho x times rho x of z times c over rho z, because this is the definition we have here. So this is the acceptance part, because UK less than this, then we will get 1. So we will get, that's the probability. So of course, given z, w is 1, actually depends on this case. So if we multiply this part, or not multiply, like just put this back, plug it back, then we will get something just cancel out. And then here will be c times rho x of z over rho of w1. Okay, be careful. Both these two are density functions, so which means they should be proportional to each other. So rho tilde x and rho x. So because each of them should be proportional to each other, then we know this one should be the same. So which means C actually exactly equal to the rho, like the probability of acceptance. So we know when we try to use this idea to generate that, we will get the desired density function. So the probability of acceptance is C, because these two should equal. Then we can make sure both of them are the density function. So that's the ideal. Okay, we want to verify this one is equal to this rho x of Z. So you can see based on these two are both the density function, so they should be proportional to each other with the same or common space. So that's what we have. This probability of acceptance actually is your C. So this tells us your C actually determined like how large the sample size you need to have, because you cannot say I want to generate 1,000 instance for X and then you just use 1,000 Z to generate this, because it's impossible. Not all the Z will be accepted. Then you need to consider how to try to generate this. So that's the probability of C. So let's see. So here we have some idea, like just as Xia mentioned, like how do you know the density function? You have to know, otherwise you cannot to get it. So this is the one we want to have. We need to know both two density function. One is the one you want to generate. The other is the one you want to use to generate this X. Okay, and actually sometimes you can, the interesting part of this rho Z is you don't need to like say I have that directly, but you will kind of to do it by the inverse transformation method. So use that to generate your rho Z. And another like disadvantage of this one is the number of capital N. So which means you want to get is the little n, but you maybe need to generate the sample size is capital N such that you can receive or accept little n samples. So your efficiency, actually, you can consider the exponential, like the expectation of your capital N should be N over C. So which means if you want to generate 1,000 sample, like 1,000 instance for X, they may need to do like 1,000 divided by C. That's the constant you want to generate. Okay, so let's see one example here. So suppose, so this one is a little bit complicated, okay? But this is trying to give you some idea about this acceptance rejection method. So for example, if you want to generate this xi follows the standard normal distribution. Okay, we have the density function, but this one is we cannot find the cumulative distribution function analytically. And we cannot do the we can do the inverse if we use the numerical one, right? So here, let's try to consider another way. So here we introduce three different kinds of three different like random variable, T, U, and V. All of them come from the standard uniform. Okay, and we first try to generate one exponential function, and this will be our Z. So which means we will try to generate X with this Z. And how can we do this exponential function? As use the inverse transformation. So consider we just do exponential with lambda as 1. So that's one. Here we don't have lambda, so it's just negative later log of tk. The first step, is that okay? All right. Do you have any questions? Like if we try to use the exponential function to generate standard normal? So standard normal actually is on the sample space is negative infinity to infinity, right? But what about exponential? exponential should always be non-negative, right? So that's why here you can see this is the original one, negative infinity to infinity. But for the exponential, it can only do is on the part which is negative, non-negative. So that's why here we should try to convert this common sample space to the same as this exponential function. So we're trying to do is take the absolute value of that. So we will consider times 2. So that's why this will be the root 2 over pi instead of 1 over root 2 times pi here. So this will be z is from 0 to infinity. Okay, and then this is rho of x. And what is the density function of exponential? Lambda e to the negative lambda, right? Is that okay? What is, okay, yeah, actually we have this here, the exponential. Okay, but I think this part is very, sorry, this part is very important. Then let me try to show you some derivation here. So to make sure we have the correct way to do it. Okay, so this is the example. So let me write it down. So C for the exponential distribution. This is what we have. So rho Z, what is the density function of that? It's lambda times e to the negative lambda, so it's e to the minus 1. Right? Okay, and x. But this one we do some transformation as we just consider the x absolute value, so which means it's on the positive part. Over 2. I forgot. Okay, then let's try to combine them together. Okay, so we want to show is, okay, what is the condition here? Is we want to have this one is always true for any z. And then we try to construct that. And c is always less than or equal to 1. So that's why the very important part is to figure out this z. Okay, so let's first try to do is, of course, here all the z is from 0 to infinity. Right? Sorry. This is, I forgot C there. That's why it's not quite right. So here is plus C. Okay, the lambda x. Okay, I forgot the x. So that's why it's not quite right. So when we reach here, so how should we try to find the constant C? So C is something multiply this, okay? And we also know this is always true. So which means rho, if we put rho z here, c times the whole thing should less than or equal to 1. Okay, then we try to find, the maximum value of this one for any c. Then how can we try to do this? Is we trying to complete square. Is that okay? But is that right? We also need to add one terms, right? Because complete square here, just consider this part. So take the 1/2 out, here is z squared minus 2z. So which means we should plus and minus 1 here. And then this is z squared minus 2z plus 1 and plus 1/2. Right?
Yes.
Okay. Okay, then this tells us what? So for what value of z, this one can be the largest one? So we know when c is 1, this one has the maximum value. What is that? Is root 2e over pi, right? Because z is 1, so the whole thing becomes 0, gone. So we have root e, so I put it inside. This is the largest one. And we know, okay, so c times this rho x over z, and rho z should less than or equal to 1 for any c. Then what is the maximum value of c? So c should be 1 over this 2e over pi, so it should be pi over 2e. And then of course this one is less than 1. Is that okay? Sorry, when z is 1, so z is 1, comma, this has the maximum value.
Professor, is it root 2e by pi?
2e by pi is the maximum value.
Okay.
Because, yeah, this is 2e by pi, sorry. Is that not so clear? 2e over pi.
Thank you.
Okay.
Professor,
Yeah.
can you please repeat the last line in blue?
Okay, sure. So this is the condition. We know this is always true. So this one should always less than or equal to 1 for any z. Is this okay? Because this is what we are given here. So c should be some number such that this c rho times a rho of z, rho x of z, less than or equal to rho z, because I moved the rho z to the left hand side, so this will be less than or equal to 1.
Yes.
Okay, so then we know what is the maximum value of this one is this 2e over pi. So which means actually what I try to do is find the maximum value of this ratio and then figure out what is the largest c it can be. Because when we find the maximum value and c times that is still less than or equal to 1, then we don't need to worry about any other c value. So that's why c should be less than or equal to 1 over this 2e over pi. So we get this is root pi over 2e. That's the case.
Okay, thank you.
No problem. Okay, then we can go back here. So, not here. So that's why you can see we get c is root pi over 2e. We times this case. So actually times the whole thing. We just make sure this one is the exponential of some complete square case. Okay, and then of course, because the maximum value of this one is 0, so the whole thing will always be less than or equal to 1. So we get that's the case. But what I try to show is the derivation I give to you is the way how we can find this c. That's the case. So we have c times the whole thing less than or equal to 1. Then we can try to generate that. Okay, so we just calculate this, and then this is the one. So which means we generate this ck based on tk, and then check this with comparison with some uniform one, so uk. When this is true, so it's greater than or equal to that, then we can consider I as I plus 1 and xi. Be careful here, because the original xi should be plus or minus. So that's why we need another vk here to determine the sign. So pk, if it's greater than 0.5, we consider it's positive. It's less than 0.5, then we consider it's negative. So we can try to have the sign. So it will be plus or minus ck. Then we can have our xi follows the standard normal distribution. Is that okay? And then the efficiency here, or like the probability of acceptance, will be root pi over 2e. It's about 76%. It's not so bad. Okay, so this is one example to generate the standard normal. It looks very complicated, but actually this illustrates the idea of the acceptance rejection method. So actually, the cases you first try to generate is the exponential one. But how can we try to generate the exponential one? Is we use one standard uniform random variable to generate the exponential, use the inverse distribution transformation. And we can generate this exponential because if we just consider uniform, only what we can do is to use the inverse transformation to get the standard normal, because these two have two different sample space. So here, but if we have exponential, we have the sample space is from 0 to infinity, not negative infinity to infinity. So that's why we're trying to consider, say, let's flip it, or just consider to make it still on the sample space 0 to infinity, then we can have this density function. And then can calculate the ratio of this density function. We get to find the value of c, we can choose that's the maximum value we can reach. And then we make sure this one is less than or equal to 1. And then we will try to get this value, plug zk inside, compare with another uniform random variable. And of course, this one should independent from tk, okay? And then we get that case and try to choose compare. If it's greater than uk, we accept it. Otherwise, we are declined. So decline this one. And here we still want is the standard normal. So that's why we need to make sure it can be positive or negative. So that's why we introduce another one, bk. And this bk is the one to control the sign. So if it's greater than 0.5, it will be positive. Less than 0.5, it will be negative. So that's why this one will give you like plus or minus dk. You can generate the standard uniform, a standard normal. Okay. All right. Then let's see I think we have